Hello and welcome to this webinar on JBoss Data Grid. Basically going to look at JBoss Data Grid for extreme performance, scalability and availability. Basically this is part of a webinar series that we're running at C2B2 to look at in JBoss Data Grid. Part one is looking at why data grids give scalability, performance and high availability. Part two next week is looking at installation, configuration and development of JBoss Data Grid, and finally the week after that we'll be looking at testing and monitoring with JBoss Data Grid. So why is this important? Essentially reliability, availability, scalability and performance are prerequisites for functionality. If we don't have reliability, availability, scalability and performance, then obviously if your application is not available, then that application is no use to your users, and it doesn't matter how fancy the functionality is, then the application is unavailable. So one of the main problems in performance that in Java applications is latency. Latency is defined as essentially the time delay in requesting an operation and it being initiated. What we're going to do is we're going to have a look at latency and what causes latency, and we can see then how data grids like JBoss Data Grid can help solve latency problems in your applications. So if we investigate sort of sources of latency in enterprise Java, one of the major sources of latency is network traffic. So if we look at some of the figures here for networks, if we look at 1 gig Ethernet, 1 gig Ethernet will have a sustained data transfer rate of around 25 to 30 megabytes a second. And these are sort of numbers that we should all be aware of as Java developers. 10 gig Ethernet typically will have a sustained performance of around 250 to 350 megabytes a second. So it's not incredibly fast based on the sort of size of data that we need to process in this day and age. And I also tried to get some numbers from InfiniBand. So InfiniBand claims it's around 6 gigabytes a second. But I couldn't find any real performance numbers for real world in InfiniBand, whereas the other two numbers are from real world applications and real world networks. So the actual data transfer rates of typically installed networks that are out there now are not that particularly high. So pulling data across a network will introduce large quantities of latency into your application and reduce its performance. And this is what we see when we get the typical developer response of, well, that application was fast on my laptop, but it's not fast once we deployed it into data centers split between New York and London. And that, similar to that from the sort of pure data transfer rates of networks. And remember, those data transfer rates are sustained, so if there's multiple applications on the network, they have to share that data transfer rate. The other thing we look at is ping times. And obviously the ping time is a response. It's the time required for sort of message to transfer to and from a network component. And typically on your local machine you'll get ping times of around a few tens of microseconds. Whereas as you move across a LAN you may get 300 microseconds as you go across a LAN segment, so on your local LAN segment. And then when you move through some switches you'll tend to get a few milliseconds, and then if you want to ping another server in another data center in the UK, you might go up to a few tens of milliseconds, and in the US you will get up to hundreds of milliseconds. So, that's sort of time essentially just to get a response from that application if it was across those sort of levels of network. And this affects how you design your applications. If you have, say, 100 megabytes to transfer from application 1 and application 2, then whether you should do that in 10 calls each of 10 megabytes in size, or whether you should do it in one call of 100 megabyte will depend essentially on the network topology that's between the two applications. And this impacts how you'd architect your applications. So networks introduce latency both in the round trip times and in the volumes of data you can move. Similarly, the other area of hardware that obviously introduced latency is disk. So these are latest performance figures for various disks that I pulled off the internet just in the last few days or so. And we can see that, in the top on the sort of table that comes from Tom's Hardware, that the latest Seagate Enterprise Performance 15K disks, running at 15K RPM, they could deliver around 220 megabytes a second in sustained reads off the disk. And similarly, the latest Samsung SSDs, they'll do 540 megabytes a second, which is sort of maxing out the SATA 3 disk bus, which is around 600 megabytes a second at the moment. So these are hard limits on how much data you can shift from disk into memory on the machine. And these numbers are obviously across the whole machine. So if you've got multiple applications running on that machine, then these, this is a one-shot number, unless you obviously use multiple buses, multiple cards, and that gets very expensive. So in comparison, if you look at DDR3 memory, that DDR3 memory can deliver around 12 gigabytes a second at sustained rates. So memory is order of magnitude quicker than on the disk transfer rates. And so one of the key things to remember when you're architecting applications is that memory is fast. In fact, there's a study called the Stream Benchmark, which we've got mentioned in some of our blogs, and that looks at memory bandwidth. And the key thing in this study is it shows that for a typical machine, when accessing main memory from an application, you can get sustained memory transfer rates of around 5 gigabytes a second. And the key thing about it is that scales with the number of cores. Unlike disk access, memory access scales with a number of cores. So you get 5 gigs a second for one core. If you go up to dual core, you'll get 10 gig a second. So memory is fast. And we all know memory is fast. And memory being fast is why we create caches. And the cache, if you put in a cache into your application, the only reason you're doing that is to solve a latency problem somewhere. This is true both on CPUs and in enterprise applications. The only reason you have a cache is to remove latency. Obviously, if you could pull data from your data source at terabytes a second, then there'll be no need to put in places all these complicated cache architectures. Unfortunately, we don't live in that world yet, so we need to build a cache. So one thing we must do for performance in many applications is to cache data in memory. So if we look at some of the typical cache architectures that you get in applications, the first is a simple read-through cache, and this is easily supported through JBoss Data Grid, where your data store is typically a relational database, and you access that through JBoss Data Grid. So your application needs to get some data. The interface to JBoss Data Grid is a key value store, essentially a hash map. So you get an object through with the key of A. Essentially, you talk to JBoss Data Grid. JBoss Data Grid looks in its cache, and if the data is not available, it will go through to the data store, read the data from the persistent store, and pull that data and store it in the cache. Obviously, at that point in time, the application is just as slow as it would be without JBoss Data Grid, perhaps even slower, because we have to access the logic to read the data from the data store via the cache. However, the next time your application needs that data, it's in memory. And as we've seen, memory is fast, so the latency of accessing memory is in the nanosecond range. Now, at that point, your application will retrieve the data immediately from the cache, and your application is going to speed up. So what we've done by putting in place a cache is essentially remove that latency away to the data store. Similarly, we can do something called write-through. So in a write-through cache, what happens is you put some data in the cache. So put an object in a key B. That object will sit in the cache and will also then be written through by JBoss Data Grid through into a relational data store. Now, JBoss Data Grid supports both JPA and Hibernate to write data through into a relational database. And it does that using something called a cache writer or cache store. Now, the problem with, the next thing you can do, obviously, when the next time you get that data, then it will be fast because it's in the cache and we don't have to hit the data store again. The problem with, building a simple cache in a simple Java application, for example, using EH-cache or just a simple hash map or concurrent hash map, is what happens when you need to scale your application out. The biggest challenge then becomes, how you manage consistency. By storing the data in the cache, it's obviously now inconsistent with the database. So if we walk through this scenario, so if your application wants to get the object at key B again, as we saw, we read it through the cache, through JBoss Data Grid, and then it will sit in one node. Then if your application again accesses the same data and it accesses it on a separate node within your application, then the problem arises when we put some data in. So if we put object in, object B2, which is basically essentially an update to B, what we have is an inconsistent state. And this is the sort of clustering challenge that JBoss Data Grid solves over and above what you could do if you did it yourself or you used a simple in-memory cache. So what JBoss Data Grid does to solve this problem is it essentially splits the key space up into a number of partitions. It would be possible, it would be possible to maintain consistency by potentially fully replicating updates. But the problem with fully replicating updates is they don't scale, simply because the more nodes you add as you scale out your data grid, the more replication has to occur, and the more network calls that you incur when you do an update. And this tends to max out the network capability in the cluster. So what JBoss Data Grid does is it splits the key space into a number of partitions and spreads them across a number of JVMs. For example, in this slide we have 4 JVMs. And what happens is when an object is put into the cache using a key, for example key B, that object will just reside in one node. Then when you want to access it, you can access the key from any one of the other JBoss Data Grid nodes. And essentially, because of the partitioning and because the cluster of JBoss Data Grid nodes understands the topology of the key space, JBoss Data Grid will know which JVM will hold that value for B. And that will essentially get pulled across the network and returned to your application. Similarly, if you put another object in, say C, you may put it on one node, but because of the key partitioning, it may be moved transparently to your application onto a different node in the cluster. And essentially, you don't really need to know where it is from an application development point of view. All this partition space is transparent to your application, although there are enough hooks in there if you need to manipulate the partition space, or if you need to maybe cluster some keys close to each other, for example, if you do processing. and you need to access a number of keys that are related. However, in general, the keys will be split across the partition space, and you don't need to worry about that splitting. So essentially what happens is the keys are assigned a hash. Each one of the nodes in the cluster will own a specific partition, and the number of partitions tends to be fixed, but the number of nodes isn't. So we can actually scale out JBoss Data Grid by adding more JVMs. And this gives us a scalability of the cluster without having to do like fully replication. This also solves the problem that you can get with updates becoming out of sync, because essentially there is only one primary value for that object in the cluster. So whenever you access it, you will always access the same object. I mean, the biggest problem then occurs is obviously high availability. If we have an object in the cluster B, it's in one partition, to solve high availability, what JBoss Data Grid does is it allows you to configure how many duplicates that you want to store across the grid. And so in this case, we have a single duplicate. And what that means is that when there's a node crash, you don't lose all your data. So what will happen if there's node crash and one of the JVM dies within the cluster, then another JVM will take over and host the duplicate, the secondary duplicate. And you can have more than one depending on your levels of resilience that you require. And JBoss Data Grid is clever enough to ensure that the duplicate doesn't reside on the same physical machine, doesn't reside, and you can give it hints so it doesn't reside on the same rack in a server or data center if you're going across data centers. So configuring the number of duplicates will give you high availability in your data grid. And in addition to high availability, like we mentioned before, the number of nodes isn't fixed, just the partitions on the key spaces. So if you add more nodes into a cluster, what happens is the key space will be redistributed, and each one of the new nodes will take up some of the data within the cluster. And this has the advantage that you could then free up some JVM space to store more data. Essentially, in a partition cache like JBoss Data Grid, the more JVMs you add into your cluster, the more data you can store. For example, if we sort of scaled out to a 21 machine cluster like this, we did some experiments with a 21 Amazon configuration. So we had 21 Amazon M2 extra large memory instances. So these have essentially 17 gig of RAM. And we ran on there 3 JVMs per Amazon machine. In each one of the JVMs we ran with around 4 gigabyte of free heap. And this essentially gives us 63 cluster nodes, so 3 JVMs, 21 machines, 63 nodes, and that gives us 252 gigabytes of JVM heap available. If we then sort of take a duplicate, one per machine, sorry, one duplicate across the cluster, you essentially halve the amount of data you've got available in your JVM heaps for storing data, and that brings down the volume of data you could bring into that data grid to around 125 gigs. But we also have 42 virtual CPUs on there, so we have a huge compute capability in addition to the memory. And on Amazon at current prices, that's around $3,500 a month, so it's not phenomenally expensive. So in a data grid like JBoss Data Grid, the more JVMs you add, essentially the more data you can store. In this case, we were keeping JVM heaps down to around 4 gig for just to keep the garbage collection pause times on any individual JVM down into sub-second range. So storing large quantities of data in memory is feasible using products like JBoss Data Grid. It's also possible nowadays to get single machines with up to terabytes of RAM. I recently saw that Oracle's latest Spark server has up to 32 terabytes of RAM, and it's possible to buy a Dell server x86 nowadays with a terabyte of RAM for around 35k. So these things aren't horrendously expensive at the moment. So it's feasible to keep large quantities of large quantities of data, Java objects, in memory. So one of the key things around a partition cache, as we've seen, is that it provides linear scalability theoretically. Essentially what you'll hit is a limit on your network bandwidth. Because when we saw how keys are moved across the partition, it doesn't matter how many nodes JBoss Data Grid you add into the cluster, then when you access a key, then at worst case you get 2 network hops, one from your application into the JBoss Data Grid, and worst case you hit a node which doesn't contain the primary of the key that you'd like, and therefore you'll hop across the network again onto the node containing the data. But that's the same whether there's 4 nodes or whether there's 104. And it's the same for write. So we get linear scalability for data volume as we add more nodes. The other thing JBoss Data Grid provides for this data is high availability. Because the number of duplicates can be configured, we can configure what level of availability we're concerned about, whether we could lose a whole rack, whether we could lose a single machine. And this high availability, due to the secondaries in the cluster, starts allowing you to create a highly available in-memory Java data store, which is very unlikely to disappear in case of an outage, unless that outage is fairly catastrophic, in which case you should be able to reload it up from a persistent store somewhere. And access to this gives you also location independent access. You don't need to know about the partitioning when you just call the JBoss Data Grid API. When you call get on the cache, it will retrieve that object, whether it's in the database, whether it's in one of the other grid nodes. And the more nodes you add, as we've said, the more data you hold in memory. So it's possible to store hundreds of gigabytes of data across one of these data grids quite simply. One of the key concerns, though, is what happens when you need to do processing of this data. So when you access some code that needs to access a lot of the keys, if you do some simple code that uses get on the key values in your one JVM, then you'd have to pull all that data across the network. And if that data was tens of gigabytes in size, then obviously we've seen in the earlier slides that that's going to take quite a time when you look at typical network transfer rates. And then when you do the updates, store these things back, you'd have to send it all across the network again. And this, in a simple model, would obviously limit the scalability of your application because the performance for that would be slow. However, JBoss Data Grid provides capabilities to actually essentially send the processing across the network. That slide just reminds us that the network is really slow to do that sort of processing. So instead of pulling the data across the network, what you can do is actually send the processing across the network instead to the actual JVMs that host the data. So in JBoss Data Grid, what it can do is you can send code sort of MapReduce style across the data grid nodes. That code can process the data in place in memory and then just bring back the resulting result sets that you want, the small result set that you need for your application. And it can do the updates to any objects in place in JVMs. And as we saw in that large cluster with, say, 21 machines, we had a very large number of vCPUs in there. So the actual parallelization that you get, irrespective of just the network benefits, can hugely increase the speed of analytic processing on this in-memory data. And as we see from this slide, there's only one way that processors are going. This is just a quick slide to show that the typical single thread performance is starting to level off for CPUs, but in the last few years, the number of cores is going up dramatically. And there's some Spark servers nowadays with thousands of hardware threads. So being able to parallelize the processing in memory across a large number of hardware threads obviously takes advantages of modern microprocessors. So parallel is the future. So we've had a quick talk around some of the features that will give that JBoss Data Grid gives to your applications to actually allow them to sort of give high availability, scalability, and performance. So moving the data close to the processing hugely reduces the latency in your applications, and latency is probably the primary cause of poor performance in distributed Java. So sending processing across the grid gives you parallel processing, MapReduce style, and actually just the fact that you can store a lot of this data in memory will give you reduced latency. We also get extreme scalability with JBoss Data Grid. So it's writes and reads are order one, essentially constant time. We don't scale out with the number of JBoss Data Grid nodes you add into your cluster. Worst case, we get 2 hops, and that doesn't change with the number of nodes. And we get scalability into data volume as well. The more nodes we add, the more the data volume increases. And we can add nodes while the cluster is running, and the cluster will rebalance. Now rebalancing needs some planning, as it takes, it's quite extreme on the network as if, we move partitions around, but it is possible to do it. And we also, for that, so once we've now, loaded all that data in memory, we don't want it to disappear. It could take, quite a while to actually build up our in-memory data set of hundreds of gigabytes in size. So providing duplicates of Java objects across the data grid gives us no single point of failure in that, if we lose a single JVM, then we don't lose any of our data, and the grid will self-heal and ensure that the number of duplicates remains the same, those requested. One thing we also haven't discussed is write behind capability. So this is where, instead of writing through the cache, as we saw in the earlier slides, what the JBoss Data Grid will do is will asynchronously write the Java objects into a persistent store. And this allows your database to disappear for short periods of time, and the data will essentially be buffered into the data grid, JBoss Data Grid, and then written back to the database when it becomes available. Or you can also use capabilities like this for sort of consolidation writes. If you have a very high write, so a very high update rate, which can often severely stress the database and introduce large latencies due to the locks and essentially purely through the disk writes, then storing them in the data grid, and then when periodically writing them to the database can have major reductions in the number of writes hitting the actual backend database server. And also JBoss Data Grid is self-healing, so remove a node from the cluster and we don't lose any data. So that concludes the first webinar. So part 2 is on next week on the 4th of February, and this is where we'll get into a bit more into the guts of JBoss Data Grid. We'll be more showing code, installation, and configuration. And then in part 3, 2 weeks from now, we'll essentially go into more about, so you've got a data grid, basically how are you going to test that data grid and monitor it. So thank you very much. If there's any questions, we can answer some on chat. Otherwise, thank you very much.